Okay, so this is just the virtual tutorial since I won't be there for morning tutorials. We are looking at uh, maze B for the solving trig equations. We're going to look here at number 5 to start. I know they're not numbered on your paper, but this is the order of the numbers that you should have gone through. So really quick, just to show you how you should have gotten here. So you started on 1, and we should have followed the path here, 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 and then come up this way. So I'm going to go over the process for doing number 5. So if you have multiple trig functions within your equation, it doesn't matter where they are or which ones they are. The, the first step is to get everything to one side so that we can set it equal to 0. And then we'll try factoring from there to solve. And then once we have it factored, we split each factor and set it equal to 0 and solve them all. So here we've got a cotangent squared times secant. So that's like one term. Then we've got minus, and then we've got a secant. And then over on the right side, we've got another cotangent squared. So there's definitely multiple trig functions. So we need to get it all to one side. A common mistake people want to do here is trying to go ahead and factor the left because they see a GCF. Um, but that's not going to give you all of your possible solutions trying to do it that way. And it's not set equal to 0 yet anyway. So you have to always set equal to 0 first before we try factoring. Okay, so let me finer tip pen here to write this. So once I move everything to the left side, and hopefully you're doing this on some other paper or on the back of this. You're going to have this cotangent here that we're moving over to the other side. We're going to move everything to the left side. We are not going to be able to combine that with this one because yes, they both have cotangent squared, but this one is connected to this times secant. So they're not like terms. It's like having an x squared y and an x squared. You can't add or subtract them together there because they're not like terms. So when we move everything, we're still going to have those as separate terms. So we'll have the cotangent squared x secant x. And then I'm going to subtract this minus 2 cotangent squared x. And then I'm going to write the minus secant x that's already over there. And then this 2 is going to get moved over by addition. So it becomes plus 2. And now everything's on the left side, so it's set equal to 0. Now, this is not your typical quadratic form trinomial that I was showing you the X method with, that like making the X box, and I showed you the shortcut over grouping. This one is already set up for grouping because you have 4 terms. So if you look here, I can go ahead and group those 2 and those 2 together. Y'all see that? So I don't have to go through the whole any X method or finding factors or anything. It's already 4 terms, and so I'm just going to do grouping, factoring by grouping. So in the first group, what they have in common, what these 2 have in common would be the cotangent squared. Okay, so if I take the cotangent squared out, cotangent squared of x, that's going to leave me with the secant x minus 2. And then in the second grouping, I've got negative secant x plus 2. Remember, when you're factoring by grouping, you want what you're left with inside the parentheses. I'm going to erase this little bit here. You want what you're left with inside the parentheses here And then when we do the other factor, what we're going to be left with in parentheses, you want those to match. So we want to end up with secant x minus 2. So what would have to be factored from this is just the negative, because I need to change the signs. So if I pull out a -1, that would become positive secant x minus 2. This is still equal to 0. So once you have your two factors, or your two groups, and you've taken out your GCF factor, those two that I underlined in yellow match. So that means that's a factor. And then what we factored out go together to become the second factor. So this is cotangent squared x minus 1. And then the one that was the same, secant of x minus 2. Y'all feel okay about the factoring process of that? We're not done with the question, but we're done factoring. Yeah, I don't see anything in the chat, so.
Does it matter where you put the two cotangent squared, like whenever you're moving it from
No,
one side to the other?
no, I just did that because I tend to put my higher degree terms first. So since it's squared, I put it before I wrote the secant, but you didn't have to. If I had switched those and done my grouping, I would still end up with the same factors.
Okay.
Anything else about the factoring? Okay, so once you have it factored, this is the point where I call it split and solve. Okay, so I take each factor and individually set them equal to the 0 and solve. So for this first one right here, if I set this equal to 0, I would have to add the 1 to the, I have two options here actually, because technically this is a difference of two squares, so I could factor this further, but it's also a single trig function. There's only one trig term in this expression, so I don't have to factor it. I can just solve it by adding the 1 over to the other side. And then taking the square root to get rid of the square. But what I do have to remember is that when I take the square root, I have to put plus or minus in front. Okay, when you're taking the square root as part of the solving process, that's your opposite operation. You've got to put that plus or minus. If I didn't put the plus or minus, I would only get one of my or half of my solutions that I should. Um, if I had done difference of two squares to factor it, that like shows two factors, so it guarantees you would get all of your factors or all of your solutions. Doing it this way by solving, you just run the risk of forgetting the plus or minus in front. But so this one ends up cotangent of x is positive or -1. So square root of 1 is 1. So if cotangent is 1, that means tangent would be 1, because the reciprocal of 1 is still 1, right? So this is asking, where on our unit circle is tangent 1? And hopefully by now you know that that's at pi-fourths, or 45-degree reference angles. So the fact that it has the plus or minus in front means I'm going to give that solution from all quadrants. Now, this particular example has this restriction here. This is the interval where they want our solutions to come from. So 0 to pi halves, that is quadrant 1. So they only want the answers from quadrant 1. That's all we need. So we actually only need the quadrant 1 angle where tangent is 1, and that would be pi-fourths. Now for the other factor, for this one over here, I've got secant x equals 2, because I would have to add that 2 to the other side. And so if secant is 2, then its reciprocal cosine is 1/2. So where is cosine? Positive 1/2. It'd be quadrant 1 and quadrant 4. But again, because of this interval that I'm specified, that they've specified to us, I only want the answer from quadrant 1. So in quadrant 1, where is cosine 1/2? Remember, cosine's the x value. 30 starts with 3, so it's the 60 that would start with the 1/2. So that's your pi third. So pi fourths and pi thirds. So you can see that's the path shaded up here. Pi fourths and pi thirds. So we're going this way. How do y'all feel about that one? Any questions at this point? Is there a particular other type of factoring problem on here that you want to see? Y'all can unmute and talk. That's probably easier than trying to type in the chat. There's just like 5 of you in here.
Can you do number 6 with the tangent cubed?
Yes. Okay. And it's actually getting, let's see. Checking out what these tools do. Because this is, like I said, this is my son's laptop. It's not mine. Okay. That gives us a nice, like, just white page. That's better than being all jumbled up how it was, I think. No, we don't need an update right now. Okay. So I'm going to wonder if I can split screen this though. The me's on half the screen. Yeah, here we go. Okay. All right, so, oh, no, I don't want you to go back to full screen. Hang on, I'm trying to, it's like switching back and forth between tablet mode and, oh well, okay, try it. All right, so number 6. Oh my gosh. Oh, I can't click on the toolbar over here. It takes me back to that. I see. Okay, I figured it out. So we've got tangent cubed minus 2 tangent of x equals tangent. So again, think if you need to use substitution and just substitute x in for everywhere that there's tangent of x to make it make more sense for the factoring portion, that's okay. Eventually, we want to get to a point where you're not having to do that, but it will work. So you could think of this as x cubed minus 2x equals x. So these two terms are both just tangent x terms. We're going to be able to combine those. So I'm going to move that tan x from the right side to the left by subtracting. And that's going to make this minus 3 tangent of x equals 0. Now I've got everything to one side set equal to 0. And this one, oops, I did it again. I keep accidentally clicking on that toolbox. toolbar. I'm going to do GCF factoring because both of those terms have tangent of x that I can factor out. So when I factor that out of the first term, I'm left with tangent squared. Here, that would be left with just the -3. So once it's factored and each factor has only one trig term, you can split and solve. So on the left, I'm going to set this equal to 0. When I set this equal to 0, I'm going to add the 3 over. So I'm going to go ahead and just write that as equal to 3. So on the left side, this factor is, we've already isolated the trig function. So it's ready to be answered. We're ready to ask at what angle is tangent 0? Now, if we're thinking about the entire unit circle, tangent is 0 in two places. It's at 0 and pi. But we're going to come back over here to the maze and look and see this restriction that they have, or not, I don't know if you want to call it a restriction, but this interval that they want our answers to come from. So pi to 3 pi halves, what quadrant is that?
3.
So we only are going to give solutions from quadrant 3. We're only going to give solutions from pi, and it's a bracket, so we're including pi. So from pi to 3 pi halves, those are the only solutions we want. So we don't actually want this. Oops, I marked out the wrong one. Undo. We don't actually want that solution. So then on the right side, we have to take we've got the tangent isolated, but it's still squared. So we have to take the square root. I have to put plus or minus in front. It's going to square root and square are going to cancel. So then I'm going to be left with tangent of x equals positive or negative square root of 3. That's not a perfect square, so I just leave it as a radical. And I know on my unit circle that the tangent value is square root of 3 at pi thirds, reference angles. The fact that the plus or minus in there means it's all the quadrants. Doesn't matter if it's positive or negative. But our particular restriction where they want the answers from on this problem is just quadrant 3. So we just want to know in quadrant 3, where is tangent positive or negative square root of 3? It's still going to be the pi thirds reference angle. So what's the pi thirds reference angle in quadrant 3?
4 pi thirds?
4 pi thirds. So we end up with two solutions for this one. And you can see over here, that's the path that this follows here, 4 pi thirds and pi. So we're going this way. Does that help? So number 5 was factoring by grouping. Number 6, I moved everything to one side, and then it was GCF. I don't know if everybody in this call was here at the beginning of the session when I was talking about this number 1 and number 3. I actually did at the very end of 6th period today and recorded. So there is a short video posted going over those already. Because number 1, that's like a standard form trinomial factoring once you get everything to one side. But number 3, this is a difference of two squares factoring. So these have, so 1, 3, 5, those have all kind of been different types of factoring with quadratics, or quadratic form, I should say. So is there another one on this y'all want to go over, or does anybody have questions on a different, it doesn't have to be from this assignment. It can be from our quiz, it can be from a review, anything you got.
Besides like what's on here, can we go over like whatever else is going to be on the test?
Yes, so this, the mazes were just the solving trig equations portion. which is part of it, but we've also got, get back to here, um, inverse trig and just knowing you've got to know your values around. The quiz y'all took was asking specific questions about values, trig values around the unit circle. But that's because you have to really know your unit circle well and know trig around your unit circle to be able to answer these. Because once you get these factored to solve them and answer them, you have to know your unit circle. So if you want to practice some of the just knowing the values around the unit circle, we can. Or do you want to go into just the inverse trig stuff, inverse trig practice?
Yeah, like the inverse trig.
Okay. So I know there was some on the Delta Math review. Um, Delta Math here.
So are the only type of questions on the test going to be the inverse trig and the equations?
The majority, there may be like just the basic knowing the unit circle, but not very many. Now, I do want to point this out too. I know I mentioned this to people in class that were asking, but I'll show y'all once I get it pulled up here. So the skills, the types of questions that were being asked, um, I didn't realize this when I was putting them in here, but some of the higher level ones, um, I don't know if it's these, I think it's with the quadratic ones. Maybe it's these two. So when you get to the level 2 and 3s on these that are multiple levels of problems, like they get a little harder, some of them are this format where there's a value in here inside the trig function with the variable. That is not going to be on the test. There will not be ones like that on the test. We're eventually going to get to that, but you don't need to know that quite yet. You don't need to know that for this test. So when you're doing the reviews, if you want to skip like this one level 2 and 3, focus more on like level 1 where, come on, the only thing that you're taking secant of is the x. There's nothing in between the trig function and the variable is what it should look like. That's what the problems are going to look like. Now, it may be more complicated than this in terms of it could be a quadratic and you have to factor, but there's not going to be a value in here in between those, if that makes sense. And then the other type of questions some people were asking, because the Delta Math randomly generates the questions, so I don't always know exactly which ones are on there, and sometimes there's some mixed in there that I didn't realize. The other type was ones that you may need to use your calculator for. Like it's not an angle from the unit circle that we have memorized. Let me see if this might have been some of those. Like here, I don't know what this one comes out to. I have to think through it for a sec, actually. Save some time and just show solution. So yeah, so like this, where once you factor and you split and solve, you get these values like 3/4. 1/2 that we know off the top of our head, or we should know off the top of our head, where cosine is 1/2. We should know that cosine is 1/2 at 60° or pi thirds reference angles. But 3/4, that is not one that we know off the top of our heads. That's not one that we memorized on the unit circle. So this one you would have to use a calculator to find, and you get these decimal values. That's not on this test. this bottom one, like the cosine theta is 1/2, you should know that, but you're not going to have to do ones in the calculator. You're not going to have a calculator on your graphing calculator on your test. So you wouldn't be able to do that anyway. Does that make sense? Okay. So there were some of those level 2, 3 problems. Don't worry about even practicing with those or trying any more of those. Okay, so let's see, inverse. So this one, um, okay. Oh, I know. Question. Oh, this is just basic. So knowing where these values are around the unit circle. Let me see if there's any more complicated. This section. Okay, this one is all that super basic. Okay, so not that type. Let's see. These are exact values, trig equations. Okay, so I guess the delta math didn't have much of the inverse practice. So let's go look at the one from today with the textbook problems. Or you could go back to, I know that Alex that we, the worksheet when, I can't remember if that was Wednesday. I think it was Monday and Tuesday of last week. We had the actual like paper practice. So you can go back to those if you needed to. But I'm going to pull up these from the textbook since we haven't looked at any of these together yet. Okay, so for inverse trig functions, evaluate and compose. So we're looking at page 288. Let's go to that.
So what would you say is the majority of the test, or is it like split into a bunch of different topics?
I'd say the solving the trig equations. Um, but part of that is knowing your trig values around the unit circle. Like that's the last step of solving. Because once you isolate the trig expression, you have to know what angles that occurs at. Okay, so let me go to 288. No, down here. The tricky part for this, the inverse, what tends to, I think, trip people up is usually the knowing your restrictions. Okay, so just refresh on that before I even do a problem here. We've got sine, or it can be written as arcsine. So that both of those mean inverse sine. So when you see this, it's asking at what angle is sine's value, whatever it equals. Okay, so arcsine of x or inverse sine of x. So remember that both of those, when we're looking at our xy axis, they go from negative pi halves to pi halves with brackets. So anywhere here, you will not have any answers from those two quadrants. Okay, only from quadrants 1 and 4. So this is where sine values are positive and this is where sign values are negative. So if I give you a question and it says to find inverse sine of negative root 3 over 2, the fact that that is a negative value right there, a negative value for sine means that this is quadrant 4. I immediately know my answer is coming from quadrant 4 because sine's not negative in quadrant 1. And the only two places my answers are going to come from for inverse sine are 1 and 4. So then I go to, okay, it's quadrant 4. Which reference angle is sine root 3 over 2?
Thirds. Pi thirds.
Okay, at pi thirds. So I do not say, okay, what's the pi thirds reference angle in quadrant 4? And then say 5 pi thirds, because that's here. If I wanted to get to it in the positive direction, I have to travel through this no man's land over here. I cannot do that. You cannot go in this area. So you can't go through it that way. You have to get to it in the negative direction right here. So you would say it's negative pi thirds. Even though that's coterminal with 5 pi thirds, 5 pi thirds is not the right answer. Do y'all understand that? Your answer has to be between negative pi halves and positive pi halves. That's the range for inverse sine. Now for inverse cosine, or arc cosine, it's 0 to pi. And it's brackets on both of those as well. So anywhere here, this is the no man's land for inverse cosine. This is where cosine values are positive, and this is where they are negative. Then for inverse tangent, oops, forgot to write arc. Goes back to look like sine, and it's got to be quadrant 1 or 4, and it's negative pi halves to pi halves. This is no man's land, but this time it's parentheses. We can't include those values because if you think back to our tangent graphs from Unit 3, remember at pi halves and negative pi halves, that's where the asymptotes were for tangent. So it doesn't exist there. It's undefined there. Tangent, if you think about the unit circle, tangent is undefined at pi halves and negative pi halves. So you can't include those two values. Now, when we first introduced this topic, we did a Desmos classroom activity. We did that turkey. We took some formal notes when we got back from Thanksgiving break and did some practice. And throughout those notes and throughout that Desmos classroom activity, we're trying to explain why it's just these quadrants, why that is, that these are the restrictions. But if that confuses you, you don't really have to know the why as long as you understand where they exist and where they don't. Okay, it's helpful. Sometimes it makes it make more sense if you understand the why. But at this point with the test tomorrow, you don't really need to worry about the why. You just need to know which quadrants your answers can come from. Okay, so now do y'all kind of Do y'all get where the inverse answers can come from for those three? Want to go try
If
some of the? Go ahead, Holly.
if cosine is negative, like in the parentheses, do you still go from 0 to get to it?
Yes, because it's the cosine value that's negative over here, not the angle that's negative.
Okay.
So something like, if I want to know arc cosine of negative root 2 over 2, something like that.
Yes.
The negative is on the trig value, not the angle. So I'm not worried about, because this isn't an angle measure that's negative, it's the value. And cosine values are negative in quadrant 2. So I'm going to say, okay, I'm in quadrant 2 because this is arc cosine and it's negative. Now, which is the reference angle, or what is the angle there where cosine's root 2 over 2? And that's your 3. Go ahead.
That 3 pi-4ths.
Mm-hmm. At all your pi-4ths reference angles is where cosine is root 2 over 2. And the fact that it's negative told us that it was quadrant 2. Does that make sense, Holly?
Yes.
Okay. And I didn't mark it down here, but for the tangent, this is where when tangent values are negative, or excuse me, positive and negative. This would be the quadrants you're looking at. Okay, so let's look at then some of the problems using those. I'm gonna come back here. 1 through 13. Let's look at those. Okay, so these are basic ones. You're not having, it's just, and obviously I see the answers are here because we're in the teacher edition. But you're just asking yourself when you see this, like on number 1, inverse sine of 0, that's asking where is sine's value 0 between negative pi halves and positive pi halves? Because sine is 0 actually at 0 and pi, right? Y'all agree?
Yes.
But we're only going to give the answer at 0 because of the restrictions. Pi would be over here where I scribbled out through quadrant 2 and 3. We don't give inverse sine answers from over there. Okay. So like number 3, arc sine root 2 over 2. At what angle is sine's value root 2 over 2? The fact that it's positive tells me it's quadrant 1, because it's got to be 1 or 4 for arc sine. So I know I'm in quadrant 1, and I know that it's root 2 over 2 at pi-4ths. So does that first section make sense? Those kind of straightforward ones? The ones that aren't compositions? Yay, nay?
Yes.
Okay. All right. So then the other part for this, so 17, 21, 23. Let's look at those. All right. So this section down here. All right. This one is asking you to sketch the graph for each of these. So this is a type of problem, making sure you understand that the arc or the inverse is switching the x and the y from the original parent function, which we did do this in our notes. So, and I'm not going to take the time to sketch these out. So let me see if I can just pull them up for you here. It says chapter 4, answer appendix. Yeah. I thought it would give me the option to go straight to the appendix, but maybe not. Maybe I need to flip through. Oh, that's not the index I want. Yeah. I might have to just show them to you by hand if I can't find this index. Do anything. Actually, I don't need to show them to you by hand. We have them in our notes. Let me just pull up our notes. So I'm going to go to our completed notes. That's practice. Okay, so inverse trig notes completed part 1. I'm on a call, baby. Go talk to daddy, babe. I'm busy. Close that door, please. Okay, sorry. See here, zoom in. Sine's original graph, the wave, the sinusoidal wave is here on the left. And this shows like where those red dashed lines are drawn is where we're restricting it so that we're getting a piece that would pass the horizontal line test so that the inverse is a function. So on the right, this is the actual inverse graph. So it's taking that little piece of the restricted sine graph and switching the x and y's. So your y's were -1 to 1. On the inverse, that's your x's that go -1 to 1. On the original graph, your x's were the radian values, the angle values with pi. And now on the inverse, those are your y values. So it goes from -pi halves at the bottom to pi halves at the top. And it's just that increasing curve left to right, kind of similar to like the shape of like the cubic, but it stops. It has endpoints. Okay, so that's the graph of inverse sine. And then we looked at and talked about the same thing with inverse cosine. Here's that one. So the cosine graph here on the left, we have to restrict it to just this piece outlined with the blue so that it would pass the horizontal line test so that the inverse is a function. So if I switch that again, what was the range -1 to 1 for the inverse becomes the domain. Left to right, -1 to 1. Now notice how the original function, the where that dark blue line is traced over it, goes from 0 to pi. So it's all to the right of the y-axis. On the inverse, this goes up from 0 to pi. So it's all above the x-axis because you see the x and the y are switching. Okay, and that one is decreasing left to right. And then your tangent, this is the parent function on the left. We restrict in between those asymptotes. So if I switch x and y, if I switch those to create the inverse, Now those vertical asymptotes become horizontal asymptotes. Okay, so those were just looking at, I already forgot the page, I think it was 299. No, 289. Back to those. Yeah. Okay, and then the next ones. Pull it back up. 29 through 45. So here, this section, 29 through 40. Okay, so this gets into the part that I think tends to be more complicated for y'all. It's the composition, where you have one function inside another. I am in the middle of a call. Take it and leave. Go talk to daddy if you need something. Sorry, my kids keep interrupting, even though they should be in bed. Okay. All right, so we can do any of those. Is there a particular one? You're not, the ones 39, 40, I don't think we listed those as ones to do. Oh, I guess we just said the whole section, but you're not going to see ones as complicated as like 38, 39, and 40 on the test. So
Can we
besides
do
the
37?
37, sure. All right. All right, so on 37, we want to work inside out. Got sine of 2 inverse cosine of root 2 over 2. So what, again, when I say work inside out, I mean we're going to do this inner function first. We'll worry about this sign later. Okay, so we're going to focus on just what's in that, what I boxed in. So the first thing I'm going to do, this is multiplication. Oops. So I'm going to solve, if you do order of operations, you would do your trig function first. So I'm going to do inverse cosine of root 2 over 2. So that is asking, let me get a different color that cuts off that 2. So I'm actually going to do that first, then multiply by the 2, and then worry about the sign. Okay, so what's in the green brackets is asking at what angle is cosine's value root 2 over 2. Now, inverse cosine, I'm going to come back up here to this picture. It's got to come from quadrants 1 or 2, right here. The fact that it is positive root 2 over 2 tells us it's quadrant 1. So in quadrant 1, where is cosine root 2 over 2? And hopefully y'all know that that's at pi fourths. Okay, so then I've still got, oops, that 2 out front of there and the sign out here. So 2 times pi fourths becomes pi halves. And then I want to do sine of pi halves. Now this one doesn't, there's not a specific restriction to how many times. So we're just going to do one revolution, one time around the unit circle, unless they specifically say all values or between a certain interval, which this one doesn't. So what is sine's value? Oh, and going this way, there wouldn't be repeats anyway. So what is sine's value at pi halves?
1.
Yeah, it's the y value. If you think about pi halves, that's right here. This ordered pair is over 0 up 1. So sine is the y value, the 1. Does that make sense?
Yes.
Okay. Does anybody else have a different one that they want to look at from that section? I know you can see the answers there, but I can walk you through the process, talk you through the explanation.
So like when inverse sine is on the outside, or like inverse whatever the trig function is like, do they cancel out?
So when it's the same, yeah, let's look at some of those. Good question. So when you have one of the original and one of the inverse of the same trig function, sometimes they'll cancel out. Okay. So for instance, like on 29, 3, 4, the way that you look at that. So that one has inverse on the inside. So as long as that because this is the input that we're looking at right there. What we're asking about is the output. Input is domain, output of the whole thing would be range. But these, because it's a composition, it's input and output of two different things. So this first one, this is the input of inverse sine. Here, our final answer is going to be the output of the outer function. So output of regular sine. So the output of sine, if you think about your sine wave, that's this one, goes on forever, right? The input for sine could be anything, but the output has to be between -1 and 1. That's how low and high that graph goes. So this answer here has to be between -1 and 1. Okay, you can think about that as the input for inverse sine. Go back up here. Here's where we talked about inverse sine. Okay, so up here we talked about how inverse sine, your output has to be between these values. Okay, but we didn't talk about the input. On the notes, go back and show those to you. When I showed you those graphs just a second ago, get back to sine. Okay, on the inverse sine function, the right picture, you can see the domain is -1 to 1. That's input. So the input of arc sine has to be between -1 and 1. So as long as that's the case, then yes, those are going to cancel each other out. So here, oops, here in this problem, that input, 3/4, that's between -1 and 1. It checks that box. So yes, those can simply cancel each other out, and my answer is 3/4. Now that's not going to be the case every time. Like in So there's not one in that list of problems where it's the same function, like both sine, but one inverse, where it doesn't just cancel out. But we did do some, find them in our notes to show you. We did, oh, composition was part 2. So like here, the way that this one is written, the arcsine is the outer function. So now this final answer is the output of the inverse sine. So going back to that graph for inverse sine, the output has to be between negative pi halves and pi halves, which this angle, 5 pi thirds, is not between negative pi halves and pi halves. So that's why you can see in this picture, since that's not in the domain of inverse sine, over here on I drew the purple angle is 5 pi thirds, but it is in the quadrants where we can have answers. So if we change it to go where this green angle is drawn, and we just say, okay, negative pi thirds, that's going to be the same sine value there. It's just calling it a different angle that's within the correct domain. So that one, we couldn't just cancel the sine and inverse sine out and say, yeah, my answer is 5 pi thirds, because 5 pi thirds isn't in the domain. It doesn't work. Does that make sense?
So you have to just find the like coterminal angle
Yes.
that's in the domain?
Sometimes that's possible. It's not always possible. So like here was one that we did in the notes where you want to try and say, oh, cosine and inverse cosine, they cancel out. The answer's pi. But again, pi is not in the domain for inverse sine. It doesn't make sense to ask inverse cosine of pi. Pi should be an output for inverse cosine. Okay, inverse cosine's domain is just -1 to 1. So there's nowhere on the cosine graph where the trig value, where cosine's value would be pi. It's the angle would be pi, the location would be pi, not the trig value. So this one had no solution. Trying to think I think those might have been the only. So here's one where it does work, like tangent of inverse tangent of -5. Luckily, inverse tangent, that domain's all real numbers. So that -5 falls in that category. So you are able to just cancel those values out and that you have your answer. Does that help some? Let me see if I can think of, just make up some other examples that might help that, clear that up, because that is that's a common place to make mistakes. So let's say we ask for don't answer these yet. I'm going to put several different examples down and we'll go through them together. Okay, so we'll take a look at these four real quick to see if this helps clarify some things. So, quick sketch here, just to remind you, for arc cosine, our solutions are going to come from 0 to pi. Okay, so looking at this first problem, if you're not sure if you can just cancel these out, you look at this value. This, for the fact that the arc or the inverse cosine is the inner function, this 3 is the input of inverse cosine. We said before, inverse cosine, I'm going to write the domain and range up here. Domain is -1 to 1. Range is 0 to pi. So input, that's domain. Is 3 in the domain of -1 to 1?
No.
So I can't do this because and if you're not if you're ever confused on if these two pieces can just cancel out and this be your answer, just work inside out. Break it down piece by piece and try and answer the inside first. Try and answer, at what angle is cosine's value 3? And the answer is never. There is no angle where cosine's value is 3. The graph of cosine doesn't go up to 3. It goes between -1 and 1. So because this exists nowhere, I cannot just cancel those out and 3 be my answer. This has no solution. But on the next one, actually, I'm going to go catty corner to the last one I wrote, since that has the inverse cosine on the inside still. So it's inverse cosine on the inside again. So that means I'm asking myself, at what angle is cosine's value 0? Well, 0 is in this domain. So I can answer this, which means since these are inverse functions, I can just cancel it out and my answer is 0. All because 0 was in that domain. I'm allowed to have that. Does that make sense? Yes, no, maybe so. The difference in those two?
Yes, makes
Okay.
sense.
Now looking at these other two, it's flipped to where the inverse is the outer function. So I need to make, instead of asking if that value is in the input of the inverse, I need to know, because that, if I'm wondering if 3 pi, if I can, I'm wondering if I can cancel these out and 3 pi halves be my answer, that means 3 pi halves would have to be the output for arc cosine. So I need to ask myself, is this value in the range of that inverse function? So is 3 pi halves in between 0 and pi?
No.
It's not. So I cannot just cancel these out and have my answer. My answer is not going to be 3 pi halves. Now that doesn't mean there's no solution like it did in this first one. Because in this first one, we were like, never, nowhere, that doesn't exist anywhere when we tried to work inside out. But for this one, if I can't just cancel them out and have my answer, I can still work inside out and try to come up with a solution. You can say, okay, this is just plain old cosine, not inverse, just cosine of 3 pi halves. What is the cosine value at 3 pi halves?
0.
Yeah, and that's at the bottom of your unit circle. So that is 0. So I'm going to replace that. Then I'm going to still have arc cosine. So now my question is, within this range, is there an answer in this range from 0 to pi where where cosine's value is 0? Where between 0 and pi, and I can include 0 and pi, remember they have brackets. So is there a value from 0 to pi where cosine's value is 0?
Pi halves.
Pi halves. So this one does have a solution. It's just not the one that was started here, written here to start, because that was out of inverse cosine's range. So I found a coterminal angle where that's true. And last but not least, this one down here, I want to see if can I just cancel these out, arc cosine and cosine, and have my answer be negative pi fourths? So we need to ask ourselves, well, when I go to answer this, if I put negative pi fourths here, that's going to be the output of arc cosine. Is negative pi fourths in the range for outputs?
Yes. No, it's not.
Not negative. If it was positive pi fourths, yes. And I could just cancel those out and my answer would be pi fourths. But not negative pi fourths. So again, I have to work inside out. So negative pi fourths is here. But I'm not supposed to have an answer down here. What is cosine's value here at negative pi fourths, though?
Square root of 2 over 2.
Yeah, that's the cosine value. Is there somewhere up here in quadrant 1 or 2 where cosine has that same value?
Positive pi fourths.
Up here, cosine is also root 2 over 2. And that's at positive pi fourths. So positive pi fourths can be my answer. And that's because I worked inside out. I looked at just this. I said, what is cosine at negative pi fourths? And this is the answer, root 2 over 2. Then I worked the outside. I said, okay, well, at what angle is cosine between 0 and pi? Somewhere up here. Where is that the value? And y'all told me that it's at positive pi fourths. Does that help? Is that clicking a little more?
Yes.
Okay. Is there anything else y'all wanted to go over? Max, are you good?
Yeah, I'm all good.
Okay. Sierra, was there anything else?
So the test is just like inverse trig and then solving and then like the basic like
Mm-hmm.
values.
Yeah. So it's just like the practice we've been doing the past couple weeks. It's just the past couple weeks of practice. I actually think the test is easier than some of the practice we've been doing because like some of that delta math that I gave you was a little more complicated. Like we're not quite there yet. I accidentally assigned that yesterday. That's not going to be on the test. And then there was some on the reviews and the practice where I told y'all, let me pull it up, where we practice doing this with variables. I think it's here on this one. Like here, where like this one, where you had 3x as your input instead of just a number. And so we had to use x's and come up with an expressions to represent the missing sides and stuff. Like that, there's not going to be one that complicated on the test. It's going to be more like what you were seeing on those review problems from the textbook here, and from Delta Math, other than the ones that I explained earlier wouldn't be on there.
Cool.
All right, y'all feel okay?
Yeah, I was a little bit scared.
You feel better?
Yes.
Good, good. Okay, well, I'm gonna let you go then.
Okay. Thank you.
You're welcome. Bye.
Bye.